Today we're going to be looking at whether or not a data set is exponential. Exponential is sometimes a word people throw around when they say, well, it's just growing really fast. It must be growing exponentially, or it could be getting small really fast. We're not going to look at getting smaller today, but we're going to be looking at the getting bigger really fast. Is it exponential, and what that actually means? So to start off with, exponential refers to a function or a situation where something's multiplying by itself many times. In this case, what it is the variable is how many times. Okay, so 2 times 2 times 2 is 2 to some power. Well, that have to be the third power. Okay, but I could go to the fourth power. I could go to the fifth power. I could multiply it by itself as many times as I want. That's what it means to be exponential. The thing that's changing is how many times you're multiplying something by itself. So we write our functions typically something like this. Y would be equal to 2 to the x. Okay, again, the variable is how many times we're multiplying 2 by itself, and y is the output value, what we end up with. In contrast, a quadratic function. This would be the one that I would say most people confuse with it, because actually parts of the graph kind of look the same. But in a quadratic graph, what's going on is they're always being times itself twice. It's what is it that's multiplying times itself is what's changing. So the base is what we call it. The base is the thing that we can change, but it's being squared, multiplying by itself twice. If we go to linear functions are things that are growing by the same amount every time they change. The rate of change stays the same. For example, when you have a job, if you're making, say, $11 an hour, then every hour that goes by, you are making $11 more. The amount that is changing by the same. 1 hour is always $11 more. So in that case, it's not going to have an exponent. This is the one most people are familiar with, linear functions, linear relationships, linear functions here. We've got just the amount that is changing by is 2. It's just how many times has it changed by a factor of 2. Okay, so that's linear. We're going to look at all three today, but the one we're most interested in is the exponential. How do you tell if something's exponential? So I've got something here that is exponential. We'll start with this. I've got 2 to the x power, and we're going to take a look at this, but I want to go through and again tell from data. How do you tell from data what they are, the linear, the quadratic, and the exponential? If it's linear, and these are also sometimes called arithmetic sequences if you've done sequence studies before. Linear functions, if you take any two consecutive numbers, the output numbers, the y values, and find the difference, and then do the same with the next two consecutive ones, you'll get the same amount. They'll be changing by the same amount every time, so the differences will be the same. Now quadratic, this is kind of an interesting deal here with quadratic. If you take those differences, if they're not the same the first time, so if they are, it's linear. If they're not, and you take the differences of the differences, it's sometimes called the second differences. If they're the same, it turns out it's a quadratic relationship or a quadratic function. But to be exponential, you're not subtracting. You're looking at ratios. The ratio from one y value to the next, and then continuing to look at consecutive y values to see, is the ratio of them the same? So this one here that I've got, when x is 1, if this is 2 to the x, I've got 2 to the first, 2 to the second, 2 to the third, so on and so forth. The values here end up being, let me just move my face out of the way here. The values end up being 2, 4, 6, 8, 16, 32, 64. I'm not going to subtract. I'm not going to find the differences. I'm going to divide. I'm going to take the 4 divided by the 2, and then the 8 divided by the 4, the 16 divided by the 8. Consecutive ratios. And in this case, the ratios all end up being 2s, which shouldn't really surprise us because we're going 2 to the first, 2 to the second, 2 to the third, so the ratios should be 2s. But that's how you tell if a data set is exponential. If you look at the output values, the y values, and you divide consecutive terms and find out if you get the same value. If they are, then you know that you're looking at an exponential function. So let's take a run at this one here. By the way, for any of these three to work, you need to be changing by the same amount for your extra independent values. So I've got them going by ones here. Okay, you can go by ones, fives, tens, threes, whatever you want, but they need to be changing by the same amount to actually analyze this. I've got them changing by ones. My output values, my y's, 120, 180, 270. If you take a look at this here, if I was thinking, well, maybe this is linear. Well, there would be a difference there of 60. But from 180 to 270 isn't 60. So I know it's not linear just from start up. And I could go through and I could look at it and go, well, maybe the second differences are the same. So here's my first differences, and you can see, well, they're not the same thing. So then I could go through and I could take the second differences, the differences of the differences. So I have the difference between 60 and 90, that's 30. Between 90 and 135, that's 45. Okay, I already know. This is not quadratic, or these would be the same numbers, but they're not. So then I would go to, well, maybe it's exponential. For that, I'm going to go back to these numbers here, and I'm going to find ratios, 180 divided by 120, and then 270 divided by 180, and so on and so forth. And if you look here, when I find those ratios, they do end up being the same. So I know that this is an exponential function. Okay, so again, first differences, if they were the same, it'd be linear. Second differences, if they were the same, it'd be quadratic. Third differences, if they're the same, it's exponential. And if you look at the graph of an exponential thing, it's a curve like this, which actually does look like the right side of a parabola, which is why some people confuse exponential things with quadratics. But they are very different, and how you analyze them is very different. Let's look at some others here. If you want to pause this one and try it yourself, you can go ahead and do that. All right, so I'm going to take a look at this, and in this one here, first differences. Whoa, between 10 and 7 is 3. 7 and 4 is 3. Okay, this is a linear function. Okay, and if I take time, I can actually graph it out. I can plot the points, -4, 10, 3, -7, -2, 4. I can plot those points, and yes, I do get a nice line. So that one was linear. The first differences were the same. In fact, what you're finding is the slope of the line when you find those first differences, because it's changing by 1. Again, these have to change by the same amount. They're changing by 1s. So I'm finding my change in my rise divided by the change in the run is what I'm doing there. Let's take a look at a second one. If you want to pause it and try it yourself, go right ahead. All right, so you go through the first differences, and they are not the same. So this is not linear. You go through the second differences. So I'm going to go 2 minus 0, 0 minus 2, 2 minus 4, and actually it doesn't actually matter which direction you go as long as you will go the same direction for each one of them. Okay, so I went subtracting, let's see, what did I do? I went 2 minus 0, 0 minus 2, 2 minus 4. That's how I found my second differences, and they're all the same. So this does tell me it's quadratic, and if you plot the points out, there's 1, 4, 2, 6, 3, 6, 4, 4, and so on and so forth. You'll see that it fits this nice facing down parabola. Okay, so the second differences are the same. It's quadratic. So you've seen a exponential, you've seen a linear, you've seen a quadratic, and how you find out which one it is. I want to look at this question. So COVID-19. They say it's growing exponentially, which this graph does look like it. Looks like it's growing really fast here, but I suppose someone could argue, well, that looks kind of like a parabola curve too. I think most people recognize back here this does not look like a parabola. But if you just looked at this part, you went, well, maybe it's a quadratic. So I'm going to go look at the data. I've been collecting the data now for the last month and a half or so. Here's the data here. And I'm a little bit behind on this chart, but I actually have been keeping track farther than this. I went ahead and I'm going to find my ratios. Again, with exponential, you're looking at the ratio. So I did 29 divided by 15, 1.9. 35 divided by 29, 1.2. I did that for every day. And you can see now, guys, this is statistics. They're not always perfect, but they are approximately the same number. They're staying kind of in that ballpark of down there in the 1.1, 1.2, 1.3 area. There's a few exceptions, of course, way up here. That was a big exception. There's a couple of 1.5s. But I've gone through, found the ratios, and actually found an average. I added them all up. That's what this 36 is, and I divided it by how many data points I had, and I ended up with an average of 1.2. I would say, yeah, this is exponential. Okay, you can look at the ratios are approximately the same. So let me get this out of the way here. Yes, I'm going to say yes for now. I'll explain that in just a minute here, what I mean by that it is exponential. In fact, I could even take and I could write a equation, a formula to predict how many is going to be after, let's say, the 40th day. I'd put a 40 here. I could find out approximately how many people at that point have been diagnosed as having COVID-19 or the coronavirus. Now, the newspaper article I looked at said that, or claimed it was doubling about every third day. So I actually went back. As long as the number of times is consistent, so every third day, I can actually still look at numbers. So I did the ratio between every third day, so 38 divided by 15, and then down here 54 divided by 38, and so on. That's what these numbers are, every third day. I did the same thing. I added them all up and found an average just over 2, which actually goes very well with, it was the Washington Post that claimed it was doubling every third day. It does seem to be approximately doubling every third day. So this equation here wouldn't give you the amount for every day, it'd be for every third day. So you say, well, you know, still, what if it had gone through this 20 times? You'd get a number, but you have to realize that it actually would have been 60 days then that had gone by to give you that particular number. So I would say, yeah, this is exponential. But I'm going to also say this for now. What I mean by that is you should know that this is going to fit eventually what's called the bell curve, which is a type of exponential function. This is also called the Gaussian curve or the normal curve. And with the COVID-19, right now we're in this section here, which looks very, very much like just an exponential growth curve. But eventually it's going to kind of slow down and it's going to reach a peak. So these models here, like this one, it wouldn't be good forever, because otherwise it would just keep on growing exponentially forever. That's not the way it's going to work. Eventually it'll peak. We've seen this in other countries already. And then it'll go through a phase of exponential decay. That's getting smaller is what that means. So getting smaller and smaller. So that's going to be at some point kicking in. We're not really there yet. We're still in this growth phase. We're down here. So it still fits exponential growth very well right now. But this gives us hope that eventually it's going to slow down. If you are in my class, then there's going to be an assignment. The assignment's going to be in your Moodle website. I want you to take, there's going to be data sets and decide if it's linear, quadratic, or exponential. Again, linear, the first differences are the same. Quadratic, the second differences are the same. If it's exponential, the ratio from each y value to the next one is going to be the same.